Okay, today lecture is about resampling methods, and we will cover the cross-validation. There are many more methods that based on the resampling techniques. Okay, we will discuss further in the next chapter about bootstrap. Right. So cross-validation, in principle, can be used for many purposes. One of them is to provide provide an approximate of the test error. So a lot of times you don't have enough data to split into like train, validate, and test. All right. So you want to use like for those you can obtain for the training purpose, but you can use it for train and validate, right? You can use it to approximate the test error. And this is to provide a way to predict the accuracy of your model. All right. For another purposes, it can be used to tune some hyperparameter lambda. These are hyperparameter of your model. This lambda is often associated with model complexity. Mm. Okay, like before you run a model, you need to predefine these parameters first. But then, in order to do that, you need to select some degree of optimality in this parameter. Like you want to choose an appropriate value of lambda, and that can be done by using the cross validation. Okay. Resampling techniques. Okay, a resampling technique is actually a process of like draw samples from a training set for several times. Okay. And this is the process of how to get resampled data. Okay, like you have suppose these all of these points. These are each samples. All right. So resampling technique is to at one instance you draw these samples. All right. And another realization. All right. Another realization. You draw the sample again. And these set, the green and the blue set, probably they are not necessarily the same, all right? And for each resample data set, you fit the model to the blue and the green one. Okay. So the goal of the resampling technique, because we would like to get some information that cannot be obtained from fitting the model only once by using the whole data set, the red one. Okay. So this method was in the past was kind of limited of usage because of the computational power of the machine. But right now it becomes very feasible, right? Because nowadays you have a fast way of computing things. You have many core processors. You have GPU that allows you to process of these repeatedly, sampling process. It can be done with a less amount of computation power. Okay. So this is a resampling method definition in general. Cross validation, bootstrap. These are two examples of them. All right. Today, today this lecture will talk about cross validation. This is as I said before, we will use it to estimate the test error, or another usage is to choose hyperparameter that reflects the model flexibility or model complexity. Oh, sorry. I should, okay, I should, hold on. Oh, this is, so sorry, this is the old slide. I need to get the, hold on. Let me get the, because I updated the slide. Let me see. 17 Jan. Okay, yes. Did I give you this version? Okay. Okay. All right. Now, for the cross validation, all right. We have two quantities involving model quality. The first one is the training error rate. This is the average error that you obtain from the trained model evaluate on the trained data set. Does it move? So I have this problem with the screen that sometimes it freezes. Okay. So in the process of developing a model, all right, you have a training data set, all right, and of course, ultimately you prefer to have the test set. These will be used to generalize the quality of your model. So the training data set is of course for the model estimation purpose. In order to get the parameter of the model, right, that optimal in some sense, you up to the estimation formulation. Okay, so when you once you get the model, right, with the parameter theta or beta, so when you evaluate it back on the training data set, this is called training error rate. Okay. But in order to use this model, you hope that okay, when it will be applied for the unseen data set, right? This is some new information. You want this model to generalize well on the unseen data. So that's why test error rate would be more useful in order to benchmark your model. All right. The keyword is these will be evaluate on new observation. These data set, the pink one, will not be used in part of model estimation process. Of course, the training error and the test error rates, these two quantities can be different. All right, it depends. It depends on the model. It depends on the setting of your DTP. Sometimes training error can underestimate or overestimate the test error rate. But most of the time is underestimate. It's underestimate the test error rate in the sense that when you evaluate, okay, of course the error rate, the lower the better, all right? So you think that, oh, your model perform well if you look at the training error rate, but when you evaluate it on the unseen data set, generally the test error rate will be bigger. So the cross-validation process here will be used to approximate the test error rate using the available data by splitting the data into the training and the validation set. And we have three approaches here. Validation set, leave one out, cross-validation, and k-fold. Okay. So these three approaches only different by how you partition or split the data into trained and validation set. So in this diagram, I'm going to use the blue color to represent the training set and the validation set by the orange color. All right. The first approach, okay, on the left-hand side, the validation set approach, or we also call it holdout approach. So it's based on the one random splitting. Suppose I have the data that labeled by the sample index, from 1 to big N. All right. The holdout approach is I can shuffle the label. I shuffle into 7, 8, 10, you know, 121, blah, 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 11, all right? I shuffle random, and then I just split it. I split portion into train and validation. Okay, and of course, one time when I split it once, I get these two sets, all right. But if I perform a holdout again, I get a different, all right, different train and validation sets because it's based on the random splitting. The approach 2, we call it leave one out, leave one out, or LOOVC. This is explained by the middle graph. This is the this will split the data into two sets, but it will be done several times. So the term leave one out, it means that you leave one sample. That explained by, I want to zoom in, but I'm not sure if it's gonna freeze it. Okay, it's okay now. So you leave one, the orange one, for validation, and the rest for training. Okay. So how many possible splitting? Of course, is n. All right. Then what do you do with these data sets? For one instance, when you leave one sample, you're gonna use the blue one for estimate the model. All right, and then, okay, I represent it with the theta, and then you're gonna evaluate the performance of the trained model based on the one that you left out, or the green one, the beige color, the pink one. Okay, so this is for one iteration, and for the second iteration, you leave the second sample, and then you do the same. You merge all the blue samples for train, evaluate on the pink sample, and continue the process for n times. All right. So in the leave one out cross validation process, what you have is that you're gonna have M1, M2, M big N. You're gonna have the trained model, all right, that use different end training data sets. Each trained model will be evaluated on the left out, right, on the left out data set, and which means that when you evaluate it, let's say you use MSE to indicate the model accuracy. So basically, you're gonna have MSE1 MSE big N. All right. In the leave one out cross validation, what you would do is that the MSE from the leave one out cross validation would be the average of these MSE, average based on these big N. The last one, this is called K-fold. K-fold based on the splitting that instead of leave only one sample out, first first you partition the data into K folds, K blocks, all right? But before you make a partition, you shuffle the data first. Let's say you shuffle, this is the sample label. This is the sample 11, samples 76, and so on, right? Okay, and then you partition it into K folds. And then you leave one fold, or the pink color for validation. Sorry, my screen freezes again. Does it appear now? Okay. So for k-fold, all right, once you partition into k-folds, you leave one fold for validation, and you merge all the k minus one fold, or the blue part, as one training data set. Okay. And this is one step, all right, and you do this by, based on the blue part, this is how you get the model, train the data based on the k minus one folds, and evaluate the model on the kth fold. And in the next step, okay, you move the index of the fold for left out, okay, and you do the same, merge the blue one as a training, estimate the model, and evaluate on the validation, and keep doing this until all the k folds are used for validation. So with this process, all right, suppose you have k4, you're going to have k models, and when you evaluate it on the validation set, so you're going to have, for example, model accuracy, MSE, for k values. And the MSE of k4, so it's going to be, sorry. So the MSE by using the K4 would be the average of these K values of MSE. Okay. All right. So this is a description of the cross-validation purpose. Now let's take a look at some example. Okay, suppose you have 500 samples, and we show you 7 runs of holdout. Okay, on the left-hand side, this is holdout. Okay, so one holdout, we split into train and validate, all right? So for one line, and in this experiment, what we do is we vary the polynomial order in order to fit data point. So this is to what? So in this experiment, we try to look for what would be an appropriate order of polynomial in order to fit data point. Okay, and what we plot here is the MSE, validated MSE. On the left-hand side is based on holdout approach. And we have 7 lines, 7 colors, because these are different 7 runs. Okay. From this graph, okay, what do you see from the graph? So the validated MSE, the cross-validation error. So we can use this term as well. Cross-validation error, but this is the method of holdout. Does it vary? Does it vary according to model complexity? Yes. But it seems that you look at the knee point here. It seems that the cross-validation error is low, and now is about the same degree when the polynomial order is about 4. So this is a way to illustrate that you can use cross-validation error as an indicator to explain about test error rate. That you never know the true value of the true error rate in practice. All right, that's why you would like to approximate it. And so these will indicate that, okay, probably I can use only polynomial of order 4 in my model, because this is can be a way to estimate a generalized error. If I use a higher order, it doesn't change. It doesn't, I mean, it's not different significantly from the 4th order. Okay, so this is the purpose of performing cross-validation. But then when in this picture on the left-hand side, I have 7 lines, all right? The 7 runs. Of course, these are the value of MSE, the cross-validation errors, like based on one degree of model complexity. These are different values. Okay. So what you have here is that the result of holdouts. Okay, if you take a look at here as well. These, okay, if you look among the 7 runs, the results of holdout has high variation, right? High variation because it depends on your random splitting. Now let's take a look at the second case. The second case is we perform the 5-fold cross validation. Here, for one, if we perform 5-fold cross validation, we get one cross validation error, right? Which means this is 1/5 summation of j equal 1 to 5 of MSE j. Okay. And then in this graph, I perform the K4 validation again, and I repeat it for 7 runs. How are these 7 runs different? Thirawat, you understand the scenario of how we perform this experiment?
So we split into 5 fold, like
Five-fold.
7 times.
7 times. So why are these splitting in 5-fold? Why are these 7 runs different?
Like to diverse the randomness, like.
Yes, because it's based on the random splitting. Because first you shuffle the label of samples first, right? So in one run you sample in this way, and then you get like you get 1K4 experiment. For another run, when you shuffle the data again, it's gonna be different order of shuffle, right? And then that's why in another run you get another set of K4 experiment. So, but then when so in this graph, what you see here is actually we have 7 lines of cross validation error. Okay, but as you notice here, I don't want to zoom in because I'm afraid that the screen will freeze again. And from this, you see that the K4 has less variation. Okay, we will say, and I would like you to verify this. All right, because the cross validation error of K4, all right, is based on the averaging of K4 over K4. That's why it has less variation if you look at the different 7 runs. Okay, we'll come back to the reasoning later. And for the third case, you perform the leave one out. All right. In the leave one out, of course, after you perform it, you get one cross validation error. And these look very similar to K-fold. All right. So from this, again, what our interpretation, if we want to use cross validation to choose an appropriate polynomial order, we use CV. All right. We use CV as an approximate of the test error rate. And when we look at this, okay, we might, this is depends on you, right? But for me, I think that, okay, order 4 is good enough. So you can, I mean, your criterion here can be quantitative as well. So you can say that, oh, I'm gonna pick polynomial order that that minimize, all right, minimize the cross validation error. Okay, like the minimum one can be not exactly at 4. If you look at the graph, it can be this, all right, it can be order 7. But I mean, but of course in practice it's up to the user, because when I see here, oh, these are not significantly different, I can pick 4 as well. All right, and of course it seems that from these 3 approach of cross validation, it gives you a rough like a rough approximation of polynomial order, that like you can see the curve that has a high knee around 4th order. These results kind of consistent from the 3 approach. One thing that the leave one out is different from the K-fold is from computational point of view, because from the leave one out, it requires big N loops, right? because back here, for leave one out, you need to leave one sample out for validation and repeat this for n times until all the n samples have been used for validation. So in terms of computational power, the leave one out requires n loops. All right. And I would like you to notice that every time for every iteration, every steps of leave one out, all right. As you see here that if we look at the blue part, so if I say the data, the training data set 1 and the training data of set 2, all right, set 2, the first and the second row, these two training sets are highly overlapped because it's only different by what? By one sample, right? Like the first set doesn't include one, but the second set includes the first sample. So the leave one out training data set are highly overlapped, which means all the trained model are highly correlated as well, right? If you look in terms of theta 1 hat, theta 2 hat, okay. So the polynomial parameters estimated from train are highly correlated. When you use this theta in order to evaluate it on the validation set, what do you think? These MSE will be highly correlated as well. Okay, that's the first conclusion from the leave one out cross validation. Okay. Now we have another simulation data set where we can.
อาจารย์ครับ
Yes.
I have a question. How we specific the k ครับ you shoot 5 fold.
Oh, okay. There's a recommendation. Yes.
The more k or the less k is good also.
We will explain in the next few slides the effect of case, and we will see that actually choosing the K4. So the method of K4 is kind of an intermediate between the leave one out and the holdout approach. So choosing K4 is actually the same thing, the same consideration in order to balance between bias and variance. And of course, that's why there's a guideline of choosing this number of folds. Practical guideline, of course, will trade off between that bias variant, trade off, and also in terms computational point of view. Right now, you see that the leave one out use n loop, big n loops. How about K4? Okay, Panat. In K4, you need to estimate the model how many times? Are you there?
N divided by k.
Oh, 5-4, K4. If you perform K4, all right? If you have K4, right? This is how you split the train and the validation. You have K patterns, right? 1, 2, 3, 4, ... K.
Okay, it's a 5.
Yes, so is K basically is, so you need to train the model K times. You have K models. And you have to evaluate these K model, each of the K models on the validation set. But usually the computational cost of running this thing, like evaluating the accuracy is very minor, right? Like think about compute MSE. The formula is just take the error square. In comparison to training the model, Usually training the model use more computational power. So that's why we say that for K-folds, all the cost goes to train the model K times. So if K is much less than big N, of course, in computational point of view, K4 would be preferred over what? Over the leave one out, right? But the concept of, what about is performance? Because as I said, these cross-validation error provide a way to approximate the true error rate, right? So what about that point of view? Which one is the best? Holdout, K4 or 5-4? So I'm saying that, that is the same argument, same consideration as balancing the balance, the bias and the variance. We will see this in a bit, all right? Okay, so this is a simulation where we generate data ourselves, so we can compute the true test MSE by ourselves. Okay, we assume that we know the true F, like we the one who say that, the true F is this mathematical function, all right, and we do perform this experiment. Okay, so in this the blue graph is the true test error rate, and we compare between 10-fold and the leave one out. The K4 is the green. Let me zoom a bit. The orange is the K-fold, and the black one is the leave one out. Okay. This is one example, all right. We see the model flexibility on the x-axis. So this aspect is to look at how your model can explain the data. So if your model is more flexible, usually the model is more complex. For linear regression, a flexible model would mean that a model that contains more predictors. Okay. So the cross sign that we mark here is the model flexibility degree that corresponding to the minimum, the lowest MSE. Okay. If we look at the K4 and cross validation, K4 and leave one out, all right, it suggests that the model complexity, the optimal one should be this and that, right, compared to the true. What I would like to what I would like you to observe first is that the cross validation estimate is usually a U shape, as we say several times, all right. Is a U shape, which is a U shape versus this graph is versus the model flexibility or complexity, as I said. Which means using a more complex model is not generally a good idea, okay? Because these cross-validation error rate, that is an approximate of the true error rate, always suggests that, it's a U-shape. Like if you reach 1 degree of model flexibility, your error rate would be higher. Okay, but on the left-hand side, this graph, okay, you see that the error rate at the model flexibility that you pick and between the true one, okay, you see that the cross-validation error underestimate the true error rate. Underestimate, right? Because you think it's lower. You think that MSE is about 0.5, but actually it's about 1. Okay. Let me emphasize again. In practice, you don't know these true value of the test error rate. It's just this simulation that I'm the one who create the actual representation of F. All right. So that's why I can compute these quantity. So in the center, okay, we change the experiment in the scenario that your actual representation of the DGP is close to linear, which means the ground truth model is simple. And what we see here is that the cross-validation error suggests what? Suggests this model flexibility. All right, and again, you still observe the U shape of the cross error rate. On the right-hand side, what do you see? On the right-hand side is another scenario. The true representation F is far from linear. Is far from linear. What do you mean? What does it mean? It means that the actual ground truth is complex. So again, when you perform cross-validation, again you see the U shape, but what you have is that the true trace error rate and the cross-validation error rate also refer to about the same degree of model complexity. From this example to illustrate, all right. So when one simple fact is that the cross-validation always has a U shape, all right. When the actual representation is linear, cross-validation can suggest a model order or model complexity that is higher than is supposed to be than the actual ground truth. But when your actual ground truth is already complex, all right, we see a desirable result that the cross-validation error also suggests and model complexity at about the same degree as the true one. The detail is this. Detail is in the books as well, that they use the model of smoothing splines. All right. Remember that for the smoothing spline, the smoothing spline is how you fit the polynomial, but these functions are piecewise polynomial. All right. So you partition your interval of x, the predictor, into different intervals, and you allow the polynomial in each interval to be different. Smoothing spline you used for the term that the smoothness of the spline can be obtained by some degree, all right? And the parameter that indicates the model complexity is the number of knots for splitting interval in the spline function. So more knot would be more complex, all right? So when they vary the model complexity here, it means that they vary the number of knots. Okay. This is what I said before, right? The way you use the cross-validation, if you have, in the first scenario, if you have many statistical methods, which means you have linear regression model, all right? You have tree, all right? You have what else? You have neural network, right? You have different methods. You can use cross-validation, all right? You perform cross-validation to compare which method would have the lowest test MSE by using the cross-validation error as a proxy, as an approximate way, and an approximate value of the true test error rate. Okay, this is one usage. Okay, another usage is, of course, I said different times. You have one method, all right? One method here. I have a smoothing spline, right? Smoothing spline. But as I said, the parameter of hyperparameter of smoothing spline is the number of knots. I need to define the number of knots first before I estimate the model. And of course, these number of knots refer to different degree of model complexity. So first, I want to pick an appropriate number of knots for this particular statistical method. All right, but what I vary is the different degree of flexibilities. So now, in the second approach, in the second way of in the second usage of cross-validation, I can use CV to tune, all right, to select the number of knots, and this is the experimental results here illustrate this application of cross-validation. Okay, we will see another examples of applying the cross validation as you learn more models after this. All right. For example, in the second part of the classifications, classifiers, we have other things, right? We have the tree model. We have more, right? You can. We will see how to apply cross validation to select hyperparameter of those models as well. Okay. now this is to summarize and to answer Panat's question as well. So you see that this is a comparison between the three approaches. Okay, the method of validation set, holdout, all right, the K4 and leave one out. In computational point of view, all right, validation set would be less because how many times does it estimate the model? Sukit. Sukit is not here. Trung, answer the question.
Yes, one time, Asha.
It's just one time of estimation, right? Sukit, what about K4?
Is that K time อาจารย์
K time to estimate the model. And for leave one out, Panat, leave one out.
N time ครับ big
N
N
times, all right? And that's why we said, leave one out is computational point of view is highest, all right? What about the ratio of training samples versus validation set? Remember that, like, in this slide, I use small n as the number of sample. Okay. My notation probably is not consistent. Sorry. Okay, sometimes I use big N, or but in most textbook in statistics they use small n. Sorry. Okay. So here, if you look at the portion of training samples, of course, for validation set, there's a guideline. There's a guideline that okay, put this ratio. This is based on one simple fact, all right, that between train and validation, if you have these, I mean, if you're not in a scenario that, oh, you have so much amount of data, you know, like you have oh, this is the portion, or the portion you get, okay, you can use only exploit these resources. Of course, based on this one fact that you should know that when you estimate the model, the more samples, all right, the more reliable of your model parameter is. Remember that one to illustrate this idea is what we've seen before in the linear regression, that like the expression of the covariance of beta hat will have a factor of 1/n, which means more samples, less covariance of estimate. So this is one thing to keep in mind. I have more data set, more samples, my parameter should have less variance, and that is a good thing. So that's why the recommended ratio train to validate, like the train portion should be bigger. For the leave one out, right? You leave one for evaluate. That's why the training samples are n-1, right? For K4s, right? K4, you have 1, 2, 3, 4, 5 folds, all right? So you're gonna use 4 folds, which mean K minus 1 fold, you know, in relative to all the K folds. So this is a portion for training samples in K4. Okay, if you look at the second point of view, all right, you see that the leave one out cross validation use the highest number of the samples. Okay, now let's take a look at the I use the term unbiasedness. If you look at so all the three approach give you the cross validation, right? the method Holdout, the method LOOCV, the method of K4. And as I said, these cross-validation error will be a proxy of true test error. Okay, so so because so the indicator here I refer it to bias. Okay, bias of what? Of cross-validation error. Because these will be used to approximate test MSE, right? So for validation set, the bias, oh no, sorry, I use this degree to indicate unbiasedness, all right? So when I say low here, it means that the holdout approach often provide a high bias of cross-validation error to approximate test MSE. Okay, for leave one out is close to unbiased, which is a good thing, all right? And K4 lies between somewhere in between, intermediate. Now let's take a look at the last point of view. This is, I hope that will be clear. If you look at the variance, okay, if you look at the variance, what variance? Is a variance of cross-validation error. Okay, so in between cross-validation, the leave one out and K-fold, all right? Now, I would like to come back here again. I think it's going to be your homework, all right? Remember that for the cross-validation, LOVC, it takes the average of MSE, each evaluated from the, one sample. In K4, right? It average based on this. Okay. All right. I refer to one simple fact in statistics. All right. Suppose you have x1, x2, dot xn. All right. Like these are random variable. Okay. So if you take average, it's the same as taking finding the sample mean. Okay. Okay, now I'm going to kind of explore, all right? I would like to see the sample mean and I would like to explore the variance. So in statistics, simple statistic, what do you know about the variance of sample mean? If each of them has a variance of sigma square, if xn, x2 are from, I can say, they can be drawn from the same population. Both, I mean, all of them have the same variance. If I have the sample mean, okay, what would be the variance of sample mean? I bring up this scenario because my x1, my each x is, I mean, plays a role of the MSE here, right? Like I have bunch of values of MSE and I take the average. So I take a look at MSE as some random quantity, which means, so I take the average, right? So I want to take a look at last point of view, the variance of the cross-validation error, right? Because as I said several times, we use cross-validation error to approximate the true test MSE. But I mean, everything is random quantity. Panat, what can you say about the variance of X bar, the sample mean?
Sigma square over n. That is why LOCV is high, variance is high, because the n is less, is only 1.
Hold on. Okay. First, step by step. From basic statistics, variance of X bar is sigma square over n. Is there any assumption, very important assumption, in order to obtain this result? Thirawat.
ครับ x1 to xn are independent.
Yes, right? Very important. X, K, R, I, D. The first I is important. Independent. Like if they are all independent, if they are all independent, the sample mean, just by taking their average, the variance of the sample mean is actually deducted from the original variance of each sample. Is reduced, it decreased by a factor of 1 over n. Okay, so this is a step like averaging random quantities. Averaging effects has a benefit of reducing the variance, but what come with a important assumption that if that quantities that you make it into the sum, if that quantities are independent. Now it's going to be your homework exercise, very simple, because if you look at here again, look at the scenario where we explained your cross-validation error. What about these MSE, MSE1, MSE2, ... MSEK? Are they independent? True?
Yes, Ashan.
Are they independent? Why? Anapat, when we explain this, okay. Now look at the cross-valid, leave one out, right? We use the blue portion, the train portion, for estimate the model. But the blue portions, what happened to like all of them?
Is highly overlapped.
They are highly overlapped. So we can say conceptually that the estimate of your model parameter would be independent or would be highly correlated, Napat?
Highly correlated.
Would be highly correlated. What about now you compare it with the MSE obtained from K4? Sukit.
Is a less correlate than.
All right. Yeah, I mean, in comparison to the leave one out, right? For K-fold, all right, the blue part here are less overlap. Are less, still overlap, but less overlap, which means the theta hat from K-fold still correlated, but less correlated relative to the LOOVC. Okay, so if theta hat are correlated, your MSE are correlated as well, but with a less amount of degree. Okay, it's going to be your homework exercise. All right, now you understand these two scenarios. Cross-validation of LOCV, take the average of MSE, all right? Take average over like N, big N. For the K4, it take the average over K. So now I will ask you to confirm this fact that why the variance of the cross-validation error from LOVC would be high, generally high, right? For K4, it would be less. So from these 2 points of view, you will see that again, choosing LOCV, choosing K4, we have many aspects, all right? But these 2 aspects, the last 2 one, is actually, again, come back to bias and variance dilemma. So it's a trade-off when you choose the number of fold. So there's a practical guideline 5 to 10. You can play with this as well. Okay, you can play with like this experiment. You can see that, oh, if I increase like more number of folds, if I don't use 10, if I use 50, what's the result? Okay, I mean, from here, from this simple example, you see that I only pick 5, right? But my graph would very similar to the LOCV already, right? Which means if I pick some number more than 5, I probably would get a very similar result. All right. For Bootstrap, this is another resampling technique, but the application of it, the usefulness of this method would be more favorable if you've seen like more contents of this course first. So I'm gonna leave this later if we have some time left by the end of the course.